Hi, AP Stats class. I'm going to walk you through a lesson for today because it's a little bit of old stuff, but it's a little bit of new stuff that can sometimes get a little bit tricky to understand. So the very first thing I want to do is share my screen with you and have a look at the AP Stats website. So as you can see right now, there is a flashy new banner on the top. So everyone that ordered an AP exam and is planning on taking the AP test should plan on attending the Zoom session with Ms. McDonald on Monday the 4th. If you click here, it'll bring you to a document that will have the Zoom link in it. Please do that. If you can't make it, she's going to record the meeting so you can watch it later. For this week's stuff, we are in part 6, which is exciting because that is the very last section that we need to cover before the AP exam. And today we are going to look at how to make a confidence interval for means. We've done this before, but we're going to get into something a little bit different today. There is the most helpful document ever, seriously, that I've made you. It has a link or a flow chart of all of the different types of inferences we've been doing, all of the formulas, how to do the calculator functions. These are the ones that you are going to be learning in part 6. It's a lot of them. These are the ones you don't have to learn because of coronavirus. So if you were taking this class normally, you would learn this, but not this year. And then down here are kind of all these other random calculator functions that we've used throughout the class, all in one spot. So print it out, tattoo it, memorize it. All right, so for this week, it's going to be really helpful to read chapter 23 or at least heavily skim it. This video here is going to explain why we're doing something slightly different when we calculate inference for means instead of proportions. And hopefully you have done all of this stuff before you kind of watch me walk through the packet that we're going to do this week. So without further ado, let me share my iPad screen. So this is what you are going to be working on this week, and let's walk through it together. If you are sick of watching videos, you can just feel free to look at the filled out version of this in the class notes instead. All right, so we are going to come up with a confidence interval for the what we think the true average weight of an Oreo is. If you have 30 Oreos in your house and a scale and you want to do this with your own data, please feel free. Otherwise, you can use the data that's up here. So Oreo tells us that their average weight of an Oreo is somewhere less than 11.3 grams. And we want to see if their claim is true or not based on some data that we've collected. So we used 30 Oreos. We found the weight of each of those Oreos in grams and found that the average was 11.1921 grams with a standard deviation of 0.08 grams. So we're going to walk through the steps of making a 95% confidence interval to estimate the true mean of the Oreos. So the point estimate for this, we don't know what the real population mean weight is, so we're just going to use our weight of the sample. So we're going to say X bar is equal to 11.1921. And then just for some good practice, let's identify the following. So the population, really we want to test this and generalize it to all Oreos. The parameter that we would use to do this, if we knew the true mean of all the Oreos in the world, we would call that mu. So that would be the true mean weight. And if we actually knew what that was, we could calculate the true standard deviation and we would call that sigma. So true standard deviation. But unfortunately, we do not know those things. Instead, all we can rely on was our sample. So our sample had 30 Oreos in it. The statistic that we're going to use to estimate the parameter is our X bar, which was 11.1921 grams. Let's throw grams up there. And the standard deviation of the sample, it said, was 0.0817. So just like we've done with proportions, we need to look at the assumptions and conditions. So one of the conditions that this needs to meet is that this was a random sample, and this is important so that we can generalize to the rest of the Oreo population. So it says up here, it was a random sample. So let's say yes. This is important because, well, so we can generalize. The formula for calculating the standard deviation of the sampling distribution of X bar, we talked about this way at the beginning of part 5, but we said when we don't know the population standard deviation, we can estimate it. Sorry, jumped ahead of myself. If we knew the population standard deviation, we could use that formula to get the sampling distribution. The problem is we don't know what sigma is, but we'll get to that in a sec. So what condition must be met to use this formula? This is that 10% condition that we've talked about a lot of times. So we're sampling Oreos without replacing them. So we have to make sure that the Oreo or the sample of Oreos that we're taking is less than 10% of the entire population. And has it been met? So is 30 Oreos less than 10% of all Oreos in the world? I hope so. Check. So like we said up above, we don't know what sigma is. So instead of using sigma, we're going to use the standard deviation of the sample instead. And as we've seen before, this thing's called the standard error now. And so we're going to say this formula is Sx over the square root of n. And let's go ahead and plug in some numbers there. So we know that the standard deviation of the sample was 0.0817. And the sample size was 30. When you type this into your calculator, you should get 0.0149. And if you feel like throwing on some units, that would be in grams. So would it be appropriate to use a normal distribution to model the sampling distribution of X bar? So this is something that you should have seen in the reading that you did. So in your textbook, it goes through some conditions and assumptions for using this. So there's this nearly normal condition. We would, if we had the data, look at a histogram to see if our data looks normally distributed. For inference for means, we can only do inference if the underlying population looks approximately normal when our samples are really small. When the samples get a little bit bigger, it's okay. So down here it says when the sample is larger than 40 or 50, it's okay if the data are a little bit skewed. But if they're extremely skewed, then you wouldn't be able to satisfy this nearly normal condition. So since we don't have the data, we're going to say, well, our sample size is on the larger side, large-ish. We will assume the population distribution not a circle, is normal. All right, so now we're getting into some slightly also new territory. So normally when we are finding a confidence interval for a proportion, you guys have been using this Z star, where a 95% confidence interval, you use the 1.96 number. We've been doing that a lot. However, you should have seen in those videos and playing around with Desmos that for means, the shape of the distribution depends a whole lot on what your sample size is. So instead of using the normal curve like we've been doing, we're now going to switch, and we're using something called the t-distribution, which, as you learned through the Guinness video, was developed by a beer brewer. Kind of crazy. So this, we're going to use, instead of Z star, T star. And unlike Z star, the T star is going to change. So if you have a 95% confidence interval for something with a sample size of 20, your T star is going to be very different if you have a sample size of 40. You can't just rely on that one number. So for that, we're going to rely on either your calculator or a t-table in order to figure out what that number is that we're going to multiply by the standard error. So what t star is needed? If you click on the link for table B, you can look it up there, and I'll show you how to do that in a second. You can also use your calculator, the inverse t function, to get that value for you. But the other strange thing is we have to figure out now what our degrees of freedom are. If you want to just take this at face value and say, yep, I'm always just going to subtract 1 from my sample size, I don't really care what it means, you are free to do that. If you want to look a little bit more in depth about what degrees of freedom are, there's some suggested extensions. There's a little article you can read about degrees of freedom. But for this, our degrees of freedom would be our sample size minus 1, which is 29. So what we're going to do is we're going to hop over to our table. Let's look at this one. This is the one that it's linked to. And we're going to go down here and we're going to look where degrees of freedom, and we're going to look at the row that says 29. And we've got all these different values here. What we want to look at here is the tail probability. So if we are doing a 95% confidence interval, that means we want 95% of our data to be contained within this lower and upper bound. That means that in these tails, we would have 0.025 or 0.25% in each of those tails. So on this table, I can look in the column that has 0.025 and see that 2.045 is the number I would use. So this is equivalent to kind of saying that 1.96 number that we would use in a Z interval. So over here, we could say our T star equals 2.045. But why use that when you have technology? Another way that you can get this, and if you forget how to do this on your calculator, it's on the most helpful sheet ever, seriously, so you can look it up on there. If you go to second distribution, so second VAERS, and go down to number 4, it says inverse T. It asks you to put in the area, so put in 0.025, the degrees of freedom, 0.29, and then paste that in there. When you do that, it's going to give you the negative version of the T star number, but just ignore the negative and put in the positive version. Alternatively, if you didn't like that, you could find the positive version. I'm going to let you figure out how to do that on your own though. All right, so we're going to calculate the margin of error using T star and our standard error. So our T star, we said, was 2.045, and our standard error from the previous page was 0.0149. No. So this number, when I multiply that out, I get 0.0305. And again, if you wanted a formula for this, this is our T star times the standard deviation of the sample divided by the square root of the sample size. All right, so now we are ready to calculate the confidence interval. So just like we've always done, we're going to take the point estimate, which we said was 11.1921 grams, plus or minus our margin of error. And when we do that, we do the lower one first. We get 11.1616 all the way up to 11.2226. When we interpret this interval, we have to make sure we do it in context, and we mentioned the 95% confidence level. So we're going to say we are 95% confident that the interval from 11.16 to 11.22 grams captures the true mean weight of Oreos. The specific formula that we used, we took our sample average, so X bar, we added and subtracted our T star times our sample standard deviation divided by the square root of our sample size. All right, according to Nabisco, an Oreo weighs 11.3 grams. Does our confidence interval provide convincing evidence that the true average weight is less than 18 or 11.3 grams? So looking at our confidence interval, if we were to make this on a number line, let's go from 11.0 to 11.5. So our point estimate was at 11.19. Let's call that, I don't know, right about here, all the way down to 11.16. Oops. 11.22. And Nabisco is saying that they are reporting that their Oreos weights are actually there. So since our confidence interval does not contain 11.3 grams, we could say there is evidence that the true mean weight of an Oreo is less than 11.3 grams. And that's because our interval is below 11.3 grams. All right, so big ideas for this section. Determine the critical value for calculating a confidence interval for a population mean using a table or technology. So for that one, that's referring to how to get T star. So for this, the important things to remember are degrees of freedom, You have to use your sample size minus 1, and then you can either use the t-table or you can use technology. On your calculators, that's inverse t. And when it asks you for the area, you want to think about what confidence level you're looking at. And then figure out what the area would be in the tails. And that's the area that you would use either on the t-table or in your calculators. State and check the random 10% normal large sample conditions for constructing a confidence interval for population mean. So random, same as before, you want to make sure your samples are random so that they are generalizable. You want to make sure that your sample is less than 10% of the population. And you want to check that for making sure your samples are independent. And then the normal, large sample one, this one is the one that is a little bit different. You want to make sure your sample is normally distributed. When you have the data, you must make a histogram or a dot plot or something. You can have your calculator do it. And if this comes up on the AP exam, you have to show a picture of it. So if your sample is not normally distributed, not really normally distributed, it's okay if it's somewhat skewed if the sample is large. And usually in this case, large can be, I don't know, I think sometimes greater than 30 in some textbooks, but again, this is one of those wishy-washy stats things. When your sample is smaller than that, you want to make sure your sample really looks normally distributed. Construct and interpret a confidence interval for a population mean. So again, that formula, if you want to write it down, we use T star. Nope. We use X bar plus or minus T star with your correct degrees of freedom, whatever they may be, times your sample standard deviation divided by the square root of your sample size. And then determine the sample, number 4. We are not going to do that one right now because I think you have learned enough for this. So I'm not going to walk through these check your understandings, but I will have them filled out and on the website if you want to have a look and see what the answers are. All right. I think that is it. Goodbye.